So let's now walk through a composition example. I really want to show you the power of all of these mechanics and semantics that we've talked about so far, all coming together in this one beautiful arrangement here. All right? So we're going to start off with a concrete version of some code first. And this is really important for me, okay? I want you to get into the idea that you're always drafting code, always drafting code. So code doesn't have to be perfect the first time around or the second time around. And I want to follow Rob Pike's philosophy to heart, that we're going to discover our interfaces. So the only way to discover those interfaces is to design code in the concrete first, some concrete implementation first, even if it's just a prototype, or even better yet, when it's a full functioning program. That's going to be much, much better for us. All right? So we're going to focus on concrete implementations. Then we're going to discover those interfaces, discover those decoupling points. Remember, decoupling is all about that polymorphism, and polymorphism is all about code changing its behavior depending upon the concrete data that it's operating on. Another thing we're going to be focusing on here is how to write code in layers. I really want to make sure that we have well-defined layers of code in an API, each layer testable, and each layer focused on what's important, which is data. Remember, the most testable code is code that can take concrete data in, returns concrete data out, and that data can be tested in different scenarios. So we always want to be focusing our testability around as much of that concrete data design as possible. All right, so we're going to be incorporating all of this into this one nice composition example and go through the refactoring on how that idea of discovering interfaces work. So let's start off really with the problem that we're going to be solving. We always want to try to solve that problem in the concrete first. So here's the problem. So a client comes to me and says, Bill, you know that system that we have back there in that old machine room, that system there that we call Xenia? I go, yeah, I know Xenia. I think that's an AS400, right? Yeah, it's a big old kind of mainframe machine back there. Well, it uses some sort of proprietary database. I don't know much about it, but I just want you to know it's there. And there's some really, really valuable data in that database, Bill. And I go, okay, keep going. Tell me what's going on. Well, you know that we make money here on a system called Pillar. Pillar extends an API, and our clients write front ends, right, that consume these APIs. That's where we make our money. And Pillar has a database. It's a more traditional database. I go, yeah, I know all about Pillar. I mean, I've been here long enough. Continue, tell me what's going on. Well, Bill, we had drinks last night with our clients, and what our clients said was that if they could get that data, we were talking to them about that data inside of Xenia. And they said, Bill, if we could get that data out of Xenia and into Pillar, they want to consume that. That's worth a lot of money to them. And I was, okay, I mean, it makes sense. So Bill, do you think that we could get that data out of Xenia and into Pillar? Now, at the end of the day, what is this? It's nothing more than anything else we've ever done. It's a data transformation problem. We gotta pull some data out and put some data in. But there are a couple of issues. Like the first thing I'm going to tell my client is, if you tell me that this data has to be moved real time, I'm already walking away, right? Like the whole idea of real time is silly. So I might say, hey, can I get like 10 minutes? Can you give me 10 minutes to wake up, see what we haven't moved yet, and move it back over every 10 minutes? And they're like, yeah, 10 minutes is good. So now I've got this interesting problem. Xenia and Pillar are my problems. And there are other issues here that we need to talk about. One thing that I've come to know from developers is that they have a really hard time sometimes breaking down problems. This isn't converting things into tasks. This is literally, what are the big problems that I have in front of me that I have to solve in the right order in order to get the job done? When I think about the problems, I see really 4 problems here. The first thing is this is some proprietary database, and I've got to figure out how to connect to it. Then once I connect to it, I've got to figure out how to get that data identified and out. I mean, these are 2 big problems. If I can't do either of those things, no other problems in front of me matter. Then I've got to figure out how to connect to this. That one might not be as big of a deal. And then I got to get that data transformed, right? and then stored. Maybe that one's not such a big deal, but this one's definitely a big deal. So before I even try to write an entire program, I might be doing some prototyping here just to make sure that I can do these things and then think about that production level code. So I've got some 4 problems that are really primitive problems, and when I can solve these types of primitive problems first, what's nice is I can then start building an API that kind of is layered. So one of the things that we're going to want to do is think about what that primitive API is. What are the big core problems that we're trying to solve, and can we write an API that solves those? And then what would be nice is we build a lower level API on top of those primitives, because if these primitives are working and they're testing, unit testing well, and we build on top of it, that's a really strong platform. And then if we do the same thing with our lower level API, then we could build some higher level APIs on top of that, and our APIs are being layered and they're being tested. I see way too many developers not focusing on this layering. And one problem I see when you're not layering is when you start having APIs, functions, right, that kind of cross these barriers, you usually have big problems figuring out how to test that code. I can't tell you how many developers come to me and say, Bill, I wrote a function, but I don't know how to test it. I guess I need an interface to mock everything. And I'm always going to say there is a place for mocking, but it shouldn't be our #1 choice. Our #1 choice should be, can I pass concrete data in, get concrete data out, and fix and test it that way. And a lot of times when you have functions that are not testable, it's because the code inside of it is crossing too many of these layers. And a lot of times we need to rethink about what's in this function and maybe break it back out. All right, so this is the problem that we're going to be solving in these different layers. And I'm going to think about my primitive layer first, which is this connectivity and finding data, connectivity and storing data. So if we come back to our code here, I want us to look at this, but I don't want you to look at this code for its true implementation. That's not what's important. What's important is how we're structuring the code, how we're structuring the layers, and then eventually how we're refactoring things to discover those interfaces. So this is a pure, concrete implementation of code. And if you and I were working together and I put you on this project, I would be telling you, I want a concrete implementation of this first. Do not give me an interface at all in this code base. If you give me a code base that has an interface, you and I are going to have a problem. Focus on the concrete problem first. And right now, that's just Xenia and Pillar. So now when I think about Xenia right in here, when I think about Xenia, what do I think? I see that Xenia is a system. It has state that we have to maintain, connectivity. We've got to be able to pull out data. We have to know the last thing that we did. There's state involved in here. There's also state involved in Pillar. So my idea now is, since there's going to be something stateful about Xenia and Pillar, I think about what we can do is define a type and create a type-based API for both Xenia and Pillar. Now, I don't care about the data so much, so we're going to keep the data simple here. We're just going to define a type named data. It's just going to be a string. Obviously, there'll be more complex data transformations going on, but that's not the point of this exercise. So here is my primitive layer. It's Xenia. Xenia is going to need a host information. We're going to need timeout information. We've got to establish probably some sort of connectivity, whether it's TCP sockets or something, I don't know, right? That's the whole point. We don't know how we're going to actually talk to this thing. So we've got to break down that wall. And let's just assume right now, let's just assume for now that we've solved our connectivity issue and we've solved this problem here. Now we're going to focus on the data problem. And again, since this is going to be a primitive API, and I'm trying to figure this whole thing out, this is my first draft of code, I decide that what I'm going to do is define a method of behavior called pull. And pull's job is just to find the next piece of data. So we take that data value that we want to pull, we share it down the call stack, so we don't have any allocations there. This is potentially going to be in a tight loop. And then pull can worry about one thing: find the next piece of data. Now, I get a sense that you're probably thinking, Bill, wait a second. For every piece of data you want to call pull, what if there's 1,000 pieces of data? You're going to call pull 1,000 times? That's very inefficient. I need you to remember something. This is our first draft of code. Okay, I'm just trying to get something that works. Two, I'm not going to be optimizing for performance right now. I'm optimizing for correctness. And the correct thing to do is to solve this primitive problem. And this primitive problem is just finding a piece of data. If I can find one piece of data, then I can find more data. And if I can build on this, then I know this code base is going to be solid. Remember, readability is also about writing a piece of code where the average team member can maintain it. And that's what I'm going for right now. And if I build all of this and it's not fast enough, we'll come in and we'll try to do some optimizations. But we'll let the tooling tell us where to focus. So there it is, there's pull. Now instead of having a real implementation, I'm choosing a random number so we can simulate that we've pulled the last piece of data, or we get some sort of error, or we actually get a piece of data back right there on line 44. So guess what? I've just solved my second problem. I now know how to get a piece of data out of Xenia, this legacy database system. Now, to keep with the symmetry of the API, I decide to go with pillar as a type, since this is a system too, right? The same thing with Xenia. Let's go with a method-based API. And to keep with the symmetry of the pull, I create a method called store. You see that on line 57. Store takes that same data value we just pulled using our pointer semantics so we can store it. Now I know what you're saying again. Bill, come on, this is going to be way too inefficient. Remember something, I've got 10 minutes to make this thing happen. I don't care about performance right now. I care about getting something working. And by keeping the primitive layer API, symmetric, it's going to also lend itself to better readability, maintainability, everything. If it's not fast enough, then we'll deal with these design decisions. But right now, we just don't know if it's fast enough or not. So I'm not going to get hung up. OK, great. So I've got my primitive layer API working. There it is. Beautiful. It's now time to start focusing on that lower level API. We're going to build on top of these primitive functions. But when I start thinking about my primitive, or my lower level API, this interesting idea comes to mind. I've got these two systems that have these two unique behaviors. One knows how to pull, and one knows how to store. And it might be interesting to create a new concrete type called system that knows how to both pull and store, and it will get its behavior through the embedding of the concrete types. So if you look on the type that I'm defining on line 65 called system, I'm embedding Xenia and pillar inside of it. Not so system has the state, but because it has the behavior. Now, I honestly don't know if we're going to use this. Sometimes when you're drafting code, an idea comes to mind. You don't know if it's a viable idea yet. You don't know if you're going to use it, but you don't want to lose it. And so I might just throw this type out there because that's where my head is right now. It doesn't mean we're going to stick with it, but it's an interesting idea to use composition here to compose another concrete type with both pulling and storing. All right, but we got to get back to our lower level API. And so I decide that we're going to use a function-based API. Remember, the rule is use functions until it's not reasonable or practical to do so. We used a method-based API for Xenia and pillar because there was state. But right now, we don't necessarily have to maintain any more state. That state can be carried forth through Xenia and pillar. So now we can go back to our function-based API. So there it is, there's pull, and pull takes that Xenia value, right? That Xenia that knows how to pull, that's the system we're going to pull from. And we decide that what we're going to do is take a collection of data. This will let us set up maybe a batch pull. So we could set up a batch of pulls and then maybe a batch of stores. So we're going to take a collection of some length. We're going to range over that collection. We're using our pointer semantics here on line 74. Then we call pull off of Xenia, trying to pull as much of that batch as possible until we get that EOF or an error. And then we're done. And we return the number of actual values that we stored inside that collection. And we do the same thing for store. There's store, takes a pillar, takes that batch of values that we just pulled, and we range over using our pointer semantics, we call store, and we store it. So now we were able to do that, we were able to run some tests, and now we have our lower level API done. We've got both of these done, and the lower level API is sitting on top of the primitive API because this is calling pull and store on Xenia and pillar. But we do have an opportunity for this high level API. With the high-level API, we can do both pulling and storing in one big batch until there's no more data. So look at what we do. We define another function called copy. But we now realize that copy needs two behaviors. It needs both Xenia and pillar in order to do a copy. It needs to pull and store. And the idea of that system type now gets interesting because we composed system with both Xenia and pillar, which means with this one passing of that system pointer, we get both pulling and storing through Xenia and pillar. So this becomes an interesting idea that maybe we can leverage as we continue to draft some code. We also set up the batch size, which means we are going to have one allocation on line 96, but it's one allocation. It's not going to affect us. And then we go into an endless loop on line 98, passing Xenia and pillar, thanks to our system, through pull and store. And we do that until the entire set of data is moved for that run. Remember, we have 10 minutes. So if it's fast enough, maybe we do this in a minute every time. The code's not going to get any simpler than what it is. And now we can go in and build our application. So there we are. We construct our system value, initialize Xenia and pillar, get those connections up and running. We call copy by sharing that system. And every time we run this, it happens way under 10 minutes. And we now have a concrete version of code that's fast enough, that's easy to maintain. We have a concrete piece of code that is layered, tested, and we could put this in production. Very, very cool. But remember, we're not done yet. And as a developer, it's super important that you're able to define what done means. For me, done means two things. One, we've got test coverage of at least 70%, if not more. You're not going to get to 100, so let's just put that past us. Though the happy path should be at 100. Overall, 70% or more, that's good. And the second thing that done means to me is that we've gone and we've evaluated our concrete implementation and have asked, is this decoupled? Do we know what changes are coming? Remember, changes are about the data, and is it decoupled? Now, we haven't answered that question yet. We do have a concrete version of code. We have it running in production. We are solving the core problem that came to us, but we're not done. And the question is, what change is coming to this program? And I think very quickly we're going to find out that when we put this in production, that sales team that got us involved in this project at the beginning is going to be super excited. And they're going to come to us and they're going to say, Bill, I don't know if you realize this, but we've been working on a project named Bob. And the idea of Bob is to migrate off of that AS400. And you know, Bill, you know, Bob's also going to have a database. And it's going to be super important that we can move that data out of Bob. And Bill, I don't know if you know this, but we're about to open up a new line of business. And we're building a new server called Alice. And Alice is going to be very similar to Pillar in that business model. And Bill, you know, we're going to have to be able to move some data out of Xenia and Bob and also put it in Alice. So what's going to change? The systems are going to change. And so what we're now going to do is ask ourselves, is this something we want to decouple ourselves from now or later? Let's do the decoupling now. Remember, we only have a concrete working version of this code, but now what we can do is decouple it by discovery. Now, if we start with the high-level API, which I like to do, we see here that copy says, okay, what we need are two behaviors, right? But sometimes it's even better if we just kind of maybe look at the lower level API. Because if I start with that higher level API, that's good. But remember, our higher level API is focusing on two behaviors, but our lower level API is only focused on one. And part of that composition, something that JBD said was, start with those small interfaces and compose the larger ones. So actually, in this case, it would be better for us to focus on that lower level API first. Let's get these smaller interfaces discovered, and then we'll compose to the larger ones. Yeah. So if we look at pull, what do we see? We see that pull is focused on that one behavior, pull, and it accepts Xenia. Right now, this function says, I only work based on what the data is, Xenia. What we do is we want this function to focus on not what that concrete data is, but what it does. And we already know that what Xenia does is pull. So imagine if we could do the following. If we change this code to say, let's not do it based on what is, but on what does, we could define an interface called puller. And that would mean that we're going to call that behavior on line 75 through the puller interface. Now this code is completely decoupled and it's precise. What it's saying is, I don't care what the system is, Xenia, Bob, whatever, as long as it knows how to pull, then I can work with it. Look at that, the puller interface. And we could do the same thing with store. We could say, okay, it's not just about the pillar implementation, it's about any concrete data that knows how to store. We could define the store interface and then execute that behavior in a decoupled state on line 86 through the store interface. We've just discovered two interfaces based on the fact that we already have a concrete working implementation. Why don't we go ahead and define those interfaces now? We can come back up here, maybe we'll do it right here, and what we can say is, okay, we're going to have a type called puller. It's an interface type. It's not a concrete type. It's based on just one behavior. And what is that behavior? Remember something. That behavior was already defined. It's already working. We know it's the right behavior. We just started to discover these things. And there it is. We've got the puller interface. What about the store interface? Well, there we go again. We can define that interface. There we go. And again, we're not guessing. We already have a working implementation here, or implementation that's already in production. There we just discovered these two interfaces. We've just defined them. There they are. We changed our lower level API out. There it is, pull and store. We already know that Xenia and Pillar implement the pull store interfaces. This code works. How beautiful is this idea of a concrete implementation as your first draft, then a refactoring to discover some interfaces around that lower level API. I mean, we're not done yet though, right? Because our higher level API, which is store, is still, or I'm sorry, copy, which is still using the concrete type system. But now let's think about copy. What copy needs are two behaviors, not just pull and not just store. It needs both pulling and storing. And something that we do a lot in Go is we do this kind of interface composition where we could define maybe a new interface called the pull storer interface. That naming convention is used quite a bit in Go, the pull store interface. And that could be any concrete type like system that knows how to both pull and store, which means that now we could pass in PS here and PS here. Now we're going to talk about that in a second, but let's go and define that pull store interface. Look at this. And this is what JBD is trying to say to us. She's trying to say compose those larger interfaces. Now what we can do is define the pull store interface. And what we can do is leverage composition and say that the pull store is the composition of both puller and storer. Look at that. Beautiful. So we defined those lower level interfaces on line 26 and 30 with those acts of behavior, and then we define those larger interfaces through the use of composition, the pull store interface. And now what this says is any concrete value that knows how to both pull and store is a pull store. And we know already that a system is a pull store because of the embedding of Xenia and Pillar. Remember, we're embedding for behavior. System knows how to pull, system knows how to store, which means that we can now pass that system pointer to copy and everything works. But now you should be a little confused because if I bring down the API for pull, let's take the API for pull for a second, and let's just lay it on top of this so you can see something here. And we go ahead and we take the API for store, and I do the same thing. I just lay it on top of here for a second. You're going to notice something. PS is of type pull storer. P is of type puller. Pull is saying it wants a puller value, but we're passing PS, and the compiler is going to be okay with that. In fact, if I run this, let's see. Boom. So how is it possible that the compiler is okay with us passing PS to pull and PS to store when PS is of type pull store and not of type puller and store? Let's go back to our initial lesson around interface mechanics. The first thing remember is this. Is pull store exist? Does puller exist? Does store exist? The answer is no, they're interfaces. They are valueless. Next question, is pull really asking for a puller value? Is store asking for a store value? The answer is no, it can't. Those values don't exist. Those functions are saying, pass me any piece of concrete data, any value or pointer that knows how to behave like a store, behave like a puller, right? And isn't it true that any concrete data sitting inside of that PS interface value, that pull store, knows how to pull and store? It does. So what's really happening here? What's happening is we're not passing PS to pull. We're passing the system pointer that's embedded inside of PS over to pull. Remember, it's only the concrete data that can be passed across these program boundaries. So one thing we can do right now is kind of map out everything that we have here, because our lower level and our higher level APIs have been decoupled. We're not completely decoupled yet. There's still a little bit more work. But it would be nice to kind of trace at least where we are. So we get into main here, and what are we doing? We're constructing our system. So here's our system right here. Now, what's interesting about system is that it has a Xenia and it has a pillar. We've embedded these values inside. We know Xenia knows how to pull, pillar knows how to store, which means system knows how to pull and system knows how to store. Remember, this embedding is adding the layer of decoupling, and it's this layer of decoupling, right? This layer of indirection, I'm sorry, that gives us the decoupling. So embedding is giving us the indirection, and it's giving us the decoupling. There it is. Now, when we call copy, copy says I want to pull store. But look on line 143. We're passing the address of system across that program boundary. And when we pass the address of system across the program boundary, what happens here? Well, on this side of the program boundary, we're going to get our PS variable, our valueless PS. But what's going to happen is we really pass the system address over, which means that that's what we're storing. And we know that PS also knows how to pull and store. We just added another layer of indirection here. When we call P off of PS, we're actually calling P off of system, which is calling P off of Xenia. We got all of this indirection, which is giving us all of this decoupling. Now, when we call pull, and we pass PS, remember, we're not passing PS. PS isn't real. We're passing that concrete address again. So that means now, when we get to that pull, this also is going to say system, and that's going to point here as well, except the puller only knows how to pull. We're going to have the same exact situation with store. So you could see how we're able to use the interface variables on these function calls, because we're not really passing the interface value. We're passing the concrete data inside of it, because that's the only thing that can be moved around our program. But we do have a problem. We're not fully decoupled yet, because if I go back into main and I want to use, let's say, Bob instead of Xenia, well, system is tied to Bob directly. So this poses a problem. I can't be breaking system every time I want to use Bob, and maybe I want to run a couple copies at the same time. Now, we do have an interface called the pull store interface. Copy doesn't care what the concrete data is as long as it knows how to pull and store. I mean, one solution could be that we create multiple systems types, right? Multiple system types for all combinations that we want to work with. We could do this, but I think we're all going to be in agreement that this isn't really a rational solution, right? It's very, very tedious. And as the number of servers grow, there's too many combinations. So this isn't going to be a solution. So how are we going to solve this problem without breaking the type? Well, let's get back to composition. What's nice about composition is that this system type doesn't have to be just embedded around concrete values. System could also be the composition of the interface types. Stop a second and think about what I just did on lines 79 and 80. What this is really going to allow me to do is inject data into our concrete system. This is going to allow me to decouple the behavior at the type level. Think about that. Which now means if I go into main, we're not initializing the embedded Xenia, we're initializing the embedded interface, both puller and storer, which again now means that if I want to work with Bob data, it's as simple as constructing Bob here. That's something we can do dynamically. Now our code really is truly decoupled from all of this concrete. So let's look at this one more time and let's walk through it. We're now completely decoupled from this change. Now what's happening is if we go back to system, let's go back to system. System is now added another level of indirection. System is now based on the embedding of puller, right? That's our puller, and store. But what's interesting is that during initialization, we're going to embed a Xenia value in here and a puller in here. So we got our pull, we got our pull, we got our store, we got our store, and we added an extra level of indirection. Now we have a fully decoupled program. This is great, but there's something that I need you to do. Remember, you're always drafting code. We've got to get into our heads that everything is a draft. And one of the most important things you can do after you get a piece of code working is to perform a readability review, to validate your mental models, validate the code you have, clean it up, variable names, the ordering of things, where things are located. It's so important that you do these readability code reviews after you get a piece of code working. If you were to be working with me all day, you'd see that this is what I do, about 30% new code, 70% review early on in a project, and then that shifts as a project matures more. So let's do that code readability review. And in this case, we can start with our higher level API, copy. Now there's a couple of questions I'm going to ask myself here. And the first one is, we have the pull store interface, but how many implementations of pull store are we going to have in this program? Remember, one of the changes that we made was that now the system type, we can inject data inside of it. If we can inject data inside of system, then I don't need more than one system type throughout the entire program. And if I only need one system type, then I'm not going to have multiple implementations of pull store. And if you're not going to have multiple implementations of pull store, then that's just type pollution. So we can get rid of the pull store interface, just accept the concrete system pointer, and guess what? We are as decoupled as we were before with one less type. Now, my compiler is complaining because I have to be passing system here. PS doesn't exist, but we'll do it again. Everything will be good. So think about it. I was able to get rid of the pull store interface. It was a cool idea, composition, to grow those larger ones. But since all of that data injection is happening inside a system, and that's the only type I'm going to have, I don't need it. Now, let's talk about one other readability aspect here that's important. And it's about precision of an API. You know, having an API that is precise is really important. It helps with testing. It helps with readability. It's gonna help with maintainability. It's gonna help with debugging. I mean, API precision is everything. And it's usually during this readability reviews where we can kind of think about that precision. You know? Encapsulation really should be an area where you create this kind of precise semantic or precise behavior, right? Where we can minimize any misuse or fraud. And for me, there's a little bit of misuse, potential misuse or fraud on this API call. I mean, it's only asking for system. It's not really clear what system has to be initialized to in order for this to work. And at an API level, it's not really clear what system is all about. So imagine if we change the API, not to ask for system, but to ask for the behaviors, the actual behaviors that we needed. I mean, think about it. Isn't this a much more precise API? Isn't it clear? Isn't it saying, I need a concrete piece of data that knows how to pull. I need a concrete piece of data that knows how to store. This idea that we're going to do this data injection was cool, but it's not really making the program easier to understand. Now, because of this precision change, one of the things I can now do actually is simplify even main. Because now what I can say here is let's construct our Xenia. Look how beautiful this is. We could say let's construct that pillar. Now during initialization, we're focused just on the concrete data the way we should be. There it is. And now what we can do is pass that Xenia in. We could pass that pillar in. We could pass Bob in. We can pass Alice. We've made main a lot easier in order to code and initialize. We've made copy as precise as we can make it. And this code is still completely decoupled from all of that change. And so that code readability review stuff that we're talking about here, it's all about validating the choices we made while we were prototyping, because we're trying to get things to work. It's validating those variable names. It's validating those function names. It's validating, are these APIs precise? It's validating, do we have pollution? Yeah, I don't need system anymore. Do we have pollution? Yeah, we don't need pull store anymore. I mean, it was great while we were drafting code, but at the end of the day, once we had a working solution, we started to review this code, we realized that that really wasn't necessary. But you're never going to get there day one. This is what's critical for me. You're not going to get there day one. So remember these ideas that we talked about when we started here. A good API is not just easy to use, but it's hard to misuse. This is where if we can make APIs more precise, add precision, making them easy to understand, we're going to be able to do that and minimize runtime issues, catching them at compile time. Right? We can always embed, but you can't decompose. You saw me create the pull store interface by embedding those other two puller and store interfaces. Beautiful, right? The composition even at the interface level. We don't design with interfaces, we discover them. Create that concrete implementation first. If you could put that in production, even better. If not, if it's a good, strong working prototype, at least you have validated your ideas, you've validated your thoughts, you probably even validated some potential performance issues too with that code, because you can debug it and test it. And then we can ask, how do we decouple it? You know, how do we identify that the interface is what we need and where they go? And finally, that idea of duplication is far cheaper than the wrong abstraction. We saw that in the grouping exercise. So this is the way I really want you to start working in Go. This composition example kind of summed up a lot of what we've been talking about up till now. There's some more mechanics that we're going to talk about here, but this is, I think, going to be one of Go's clear legacies that other languages are going to be taking from Go moving forward. Just really beautiful design patterns in Go.